All right, these are the video notes for section 2.8 on linear programming. Linear programming is building off the concept of systems of inequalities. And then we attach some other ideas to it that help us understand the feasible region in the context of a word problem. So essentially we're going to get started with the same sort of thing as doing a system of inequalities. We'll get a system graph, we'll get shaded, we'll find the feasible region, we'll locate the vertices, and then we'll apply that to one more piece of the puzzle. And that's adding on the linear programming part of the problem. So let's go ahead and get after it. First of all, linear programming revolves, when it's put in the context of a word problem, revolves around constraints. So a system of inequalities implies you got limitations. Things are less than, they're greater than, they're less than equal to, they're greater than equal to. So when you talk about a real world application of that, almost anything, any business, a school, your life for that matter, operates under some kind of system of inequalities. Now you don't think of it that way, but it does. You have constraints, you have limitations on yourself. Limitations on how you operate a business, limitations on how you run a school. So you are always going to have some kind of constraint to deal with in your life, or maybe even multiple constraints, and that's linear programming. In the context of a word problem, the optimizing function is what tells you where is the best place to operate in the combination of things that you're working with. And of course, we'll tie that into a word problem at the end. You can see that in action. For starters, we're just going to kind of flash back to doing a system of inequalities, get it graphed, get it shaded, then just talk about how to use an optimizing function without any context to it. And then the last problem we'll do is put some context to an optimizing function, like what does it actually do for you? And that's how we'll work our way through the notes. So let's get started. So the process we're going to go through again is define our variables, which in the first couple problems will be done for us. Write our constraints, they're common sense constraints, graph a feasible region, find all vertices, and then optimize your function. Before we dive into the full picture, let's just do a little bit of graphing and talking about an optimizing function. So the first thing we want to do is get our constraints graphed. Of course, we can do these by just graphing by hand, which we all know how to do. Solving that equation for y. We can also use Desmos, and you guys should be familiar with Desmos at this point, but I'll kind of jog back and forth between the two and talk about what Desmos will do for us. In terms of shading, if I'm talking about where should I shade, I'm greater than 1, that's to the right. I'm greater than 3, that's up. And then less than, which is below. So greater than above, to the right, greater than above, less than below. So that would imply that I would be in here and be my feasible region. Now vertices are, again, along the border of the shaded area where the intersections of your system is going to be. So as I kind of work my way around, you'll see there's 1, 3, 6, 3, and 1, 10.5. Now just for a second, let's flash over to Desmos and talk about how Desmos would do the same thing for us. So in Desmos, we can actually get this system in and have a look by putting in the same three inequalities. Now I put in the same three inequalities, I typed them in. This time I did not actually switch this one over to y and mx plus b, I just left it as is. Desmos doesn't really care about that, so it'll take it the way it reads on paper. Your keyboard, the pop-up keyboard has all the symbolism you need. If you weren't using your pop-up keyboard, in order to get a less than equal to or greater than equal to, you have to use the option key and then hold down which one you want at the same time. But in this case, I can see it's already been graphed, and you can put them in, it'll graph as you go. And then along the border of the shaded area, the feasible region, which is this darker area in here, which we already talked about, I can go ahead and click on my vertices and see what they are. So Desmos is nice as a backup. You should be able to do it by hand, but you'll be using Desmos to do some of your work, and it's pretty simple. Things type in just as you would expect. You've got a keypad here that has all the symbols you need. You can adjust this by moving it left, right, up, down. Right now I'm just clicking and holding down. I can go home, which is a 10 by 10. It kind of recenters it. I can zoom in, I can zoom out, do whatever I want, shift it around. A really nice tool, especially when you're doing a system and there's lots going on and you want to get a quick look and a backup and make sure that all your vertices are accurate. Okay, we're going to go back to the smartboard file a little bit to keep going on with our problems. So the idea is now we've got our system graph, whether we did it by hand or we used Desmos to help us out. We've located our vertices, we've located the feasible region, and now I want to talk about an optimizing function. So the optimizing function will be given to you, and the idea is you plug your vertices into it. And so we're going to drop that down here and just use it as our guide, and then see which one produces a max or a min value. In the context of this problem, there is nothing that it would tell you except largest and smallest value. In a word problem, that optimizing function and its values would have meaning to us. But nevertheless, it's pretty simple. We just go ahead and we plug in. So So plug in, plug in, plug in. All I'm doing is putting in x and y into the equation, then I'm seeing what I get. And as far as max and min goes, smallest value min, largest value max. Pretty simple. So that'll be an add-on to the bigger systems of inequality problem. And when we put it all together, we then call it linear programming. So we look at constraints and we look at where we can operate around or even sometimes within the feasible region. All right, let's look at a couple more to continue on. So this time I'm not going to jog over to Desmos and put it in, but you certainly could put all this in as it reads. I'm just going to pop them up on a piece of graph paper. So I got vertical, horizontal, and then these two, again, I could go mx plus b for the purpose of graphing. If I'm in Desmos, it'll actually take it just like this. So either way is fine. Then I got to get my shading correct, so I got to start again and visualize a little bit. Sometimes I like to use the arrows, like a little bit of kind of just make a note to myself, greater than above, greater than to the right, above the horizontal line. I'm above here also greater than, and I'm above here also greater than. So if I'm literally above everything and I go for a common area, that common area has got to be right there. So there's my feasible region. Now, as far as vertices go, remember, it's not every single intersection you can see. It's only the intersection as you travel along the border of the shaded area. So as I do that, I'm going to be 0, 8, 16, 0, way out the end there, and then also 2.3 and 3.4. Now, Desmos would be handy here because this one I would not be able to tell exactly by looking. So if I had this system into Desmos, all I would do is go back and I would click on that and it would show me. I click on that exact spot and I would get the numbers to go with it. Anyway, once you've got it, again, it's more or less, let's plug in and see what's going on. So plugging in 0 and 8, I would get 8. Plugging in 16 and 0, I would get 64. Plugging in 2.3 and 3.4, I would get 12.6. And again, I'm plugging in here. Now, in this case, max and min, well, it says minimize only in y. Well, first of all, as far as the min goes, that's sitting here. The reason there's no max is because you can keep plugging points in that go further and further out in the feasible region, and they just keep producing bigger and bigger values because the feasible region extends out basically forever. So we can only look at what would minimize. We can't say really anything would maximize what's going on here. Okay, so a couple basic ones to just practice using the optimizing function. It's not in the context of a word problem yet. We're getting to that, so we'll show you guys that next. So what's different about doing linear programming is you're not given the system, you have to create the system. So you got to take a minute to read through the problem and decide what you want to call your x and your y. We're going to just use x and y as our variables. Set up your own constraints, again, based on what you're reading. Set up your own optimizing functions. So there's a lot of you having to do the work up front. And then once you have it, then it kicks back into graphing, shading, get the feasible region, get your vertices, plug them in, max and min, that all falls into place. But before you can do any of that, you got to create what the problem tells you. So as we read through, we're going to do two kinds of problems. We're taking a quiz. We got computation, so calculation problems, and graphing. It gives you some point values, what they're worth, and then it gives you some limitations. So 2 minutes for graphing, 2 minutes for computation, 4 minutes for graphing. You have 40 minutes to take the quiz. You have you will choose no more than 12 problems. Well, 40 minutes is a restriction. That's a limitation. No more than 12 problems, that's a restriction, a constraint. So when you're limited by something, that's a constraint. What we need to do is get all this pieced together with inequalities that would make sense. First of all, our variables, pretty simple. Typically, most problems have two things you're comparing. So I'm just doing the order that I'm reading, computation being x, graphing being y. Common sense constraints, which will be in every single linear programming problem, will be whatever your variables are greater than 0, because there's no sense to be doing negative or 0 questions. You would be answering questions. And in any word problem where we've got some kind of context that we're dealing with, 0 or negative usually will not make any sense to us. Then we've got to piece the rest together. Now there's a time constraint, right? We've got a limitation of no more than 40 minutes. There's a problem constraint less than 12, less than or equal to 12. So we're got to be under 40 minutes, no more than, which is less than or equal to. And then we just have to go back to the problem and piece things together. Like, what is the connection to time? Well, it's 2 minute computation, 4 minute graphing, so that's going to be 2x plus 4y. And then this one you don't necessarily read in the problem. Be careful, don't grab the points. We have nothing in the constraint about points. This is just really the combination of the two kinds of questions. So you're doing sum of each, whatever you choose, no more than 12. The point value has to do with optimizing. So you got to read this carefully. What is being maximized or minimized? Calculate your score. The question was, how many types of each question should I answer to get the highest score? Well, highest is going to be a max concept, so we're going for max. But how do you calculate the score? That's, of course, based on the point values. What points are assigned to each of them? So you've got 6 for your computation and 10 for your graphing. Whatever combination I would do, I plug it in for X and Y, and that would then calculate my score. Now we are set up, ready to go. We know what our variables are. We got our system organized. We got our optimizing function. We can now start working through the rest of the problem. Working through the rest of the problem is really just graphing. So here's our common sense. Now you notice how they're dashed because we're saying we're not going to operate in 0. We're not going to operate in negative. Again, I could do this on Desmos if I wanted to. You can also mx plus b, which takes about 2 seconds, and get that graphed. Also another mx plus b, get that graphed. And then we are always greater than our common sense constraints because we would operate in the positive areas of the graph. But in the other two, we're less than, which is below, so our feasible region is going to come in right here. Then we just travel around the border of the shaded area. Remember, we don't grab every single intersection like this one here and this one here. No, we got to stick to around the border of where it's shaded. And also I popped up 0, 0. In this problem, 0, 0 will not even consider because that's like saying you answered no questions, which of course would produce no score, and we're going for a max score. The ones that I will use will be the ones that pop up here along the border of the shaded area. And then my score, my calculation based on my optimizing function. It says objective quantity here, but we call it optimizing function. And what I'm going to do now is go ahead and plug in. So plug in my 3 vertices. The question was about highest score. Highest score refers to the max, so I'm going for that. That's my max value. And then finally, what combination did I do that produced it, which was 4 computation and 8 graphing. So now you can see the the optimizing function in action, what it does. It produces the calculation, in this case a score, and that can be whatever your particular problem talks about, but a lot of times max, sometimes min, and then what's your final answer. And that's it for your 2.8 linear programming notes.